You need to grab chapter 6. It's over here. I think everyone's got it there. All right, so chapter 6, this is almost gets to be kind of brain candy for the geeks when we're going ahead and calculating out series parallel circuits. So let's take a look at, we're going to kind of go through these as we're going through our circuit here. So the first thing you want to do is, to kind of interpret what's going on with the circuit. We still want to go ahead and we always want to draw our current paths and our polarities on the original circuit. So we're going to put our negative, positive, and so we're going to have all our current coming out of the power supply. It's going to come up to the first current node. Some of it's going to be going through this branch. And then make sure we get our polarities, because that's important when we start doing our test points. The remainder amount of current then is going to continue on to this current node. And some of it's going to come up through this way. And then the remainder amount of current then is going to be going through the last branch, heading up. And this current is going to come in, and then we're going to combine branches 1 and 2 at this point. So the total current here is going to be of branches 1 and 2, or 2 and 3. And then it's going to continue on, and then it's going to combine with branch 1. And then all my current is going to go back into my power supply. So now we have our current paths and polarities. Then we can kind of see already how the circuit's going. So then what we want to do is we want to combine this down into one resistor. We're going to break it all down into one resistor, and then we're going to back our way out and recalculate everything on the way back. So I'm going to be kind of spread out all over the place here, because we have to spread it out and stuff. I wish I had a whole wall of whiteboards here. So typically our first rule is that we always want a straight line. Okay, well our circuit is already straight line. We have our power supply on the left-hand side. All our components are on the right-hand side of the power supply, and they're all drawn vertically. So we're already straight line, so we don't need to do that. So our first step is what we want to do is we want to find the like components. Okay, so for example, we know that R1, 2, and 3, how are they all connected? Series. Okay, so all those three. Let me grab my other. Probably I had to hide it. Feeling on me. I thought I'll get too much blue going on in there. So what I do is I kind of start drawing boxes around the things that I can combine right off the bat. So I know that I can combine all those three. Then R4 and 5, those are also in series, so I can combine those ones. And then I can combine R6 and 7, because those two are also in series. So then I'm going to draw I'm going to be kind of all over the place, but I'm going to redraw my equivalent circuit then. So I'm still going to have 3 branches, but I'm going to combine R1, 2, and 3. So I'm just going to write in here so I know what I got. I got a combination of R1 And if we wanted to write it out, but it gets a little bit lengthy if we do it, but we'll do it on this one here. So if we did want to verbally tell somebody how this circuit is hooked up, we can say that R1 plus R2 plus R3, then that's representing that all three of those resistors are in series. So this branch here is a combination of R1 plus R2 plus R3. Branch 2 then is going to be the combination of R4 plus R5. And then our last one, branch 3, is going to be the combination of R6 plus R7. Okay? So I started reducing my circuit down to not only have 3 resistors, okay, and it's going to be equivalent to this circuit, and I'm going to start combining all my like components that are in the, either if they're all in series or if they're all in parallel. Then I'm going to put in my voltage source here, so I know that I got 100 volts. I got my current that's still going to be coming out of here. Some of my current's going to come into this current node, some of it's going to go up through branch 1. Remainder is going to go to this current node. Some of it's going to go up to branch 2, up into here. And then the remainder is going to go into branch 3. And that current is going to combine with branch 2. Those two are going to combine together, go into this current node, combine with branch 1, and then my total current goes back. Okay, and then the other thing I need to transfer over are my test points. So we know that we have test point A, that's going to be on my positive side of my power supply. And then what I like to do is I kind of like to try getting everything over to the right if I can. Because test point A is anywhere from my positive side of my voltage supply all the way over to the top of R6 and R7, to the positive side of R6 and 7. Or test point A could be considered this line, because that's all still all considered one part of that line. So test point A is here, 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 anywhere on that, on what we call next. So I just kind of like to bring it out to the right-hand side if possible. So there's going to be test point A. Test point B then is going to be anywhere along this wire here, or any one of these branches going up to the negative side of either R3, R5, or R7. So if I was looking at a circuit board and I couldn't get to the negative side of R3 for some reason, I could go to the negative side of R5 and measure test point B. Or I could go to the negative side of my power supply, or I could go to the negative side of R7. Wouldn't matter where I'm getting that test point, that reference test point. So again, I like to kind of just bring that one over. Bring that one off. So there's our test point B. Now test point C, that's within our square there. That's the one that we kind of reduced down. So once we reduce those down into one resistors, test point C is no longer part of our equivalent circuit here. So we just ignore that one. Same thing with test point, let's see, where's test point D? Same thing with test point D. Same thing with test point E. And the same thing with test point F. Okay, so all those got lost once we combined all those. If they're within that square that we drew, we're going to lose those test points. So the only 2 test points that we have then is test point A and B. Okay, so now we transferred all our information. We got all our test points. We have our voltage supply. We have our current paths and our polarities. Now our next thing is that we want to do is find out what the equivalent resistance of each one of these resistors are. So what's the equivalent resistance then of R1 plus R2 plus R3?
10 ohm.
It's going to be 10 k ohm, and we just add them together, just like our verbiage said there. So the combination of R1, 2, and 3 is going to be equal to 10 kiloohms. Okay, and the combination of R4 and 5 is going to be what? 5 kiloohms. And then R6 is going to be what? And 7.
10 kiloohms.
10 kiloohms. Okay? So now we have all the equivalents that we need for right now. We're not going to do any more calculations at this time until we get it down to one resistor. All right, so now, even though we could really work this out at this point, because we know parallel circuits and stuff, but we're going to take it into more individual steps. So when we get into complex circuits, you can see the whole procedure of it. All right, so now we have that all completed, and we want to get this down into one equivalent circuit. So now we're going to take, the combination of R1, 2, and 3 plus is in parallel with R4 and 5, which is in parallel with the combination of R6 and 7. So those are all in parallel. And we can take all those now. Since those are all in parallel, we can break those all down into one single resistor now. Know that we got 100 volts. Know that all my current is going to come out of my power supply. All my current is going to go to the equivalent circuit. Back up to my source. And so now this is going to be RT. So RT then is going to equal R1 plus R2 plus R3. I'm going to do those first. I'm going to put those, because that was our first step that we did. We combined all these first. So I'm going to put those in parentheses. And then to tell somebody that it's in parallel with something, you just use the double bar line. Okay, this just represents that it's in parallel with R4 and 5. So then we're just going to go R4 plus R5. And then put those in parentheses, because we combine those first before we put them in parallel. And then that's going to be in parallel with R6 and 7. R plus 6 and 7. And now all those, the combination of all this, then is going to give us our total resistance for this circuit. Okay? So we've already combined R1 through 3, R4 and 5, and R6 and 7. So we can just take our numbers here and put these in to our parallel formula. And we know that by just looking at this, before we even use our calculator, we know that our resistance is going to be less than what? No, not 10 kilo ohms. 5 kilo ohms. Remember, in a parallel circuit, it's always going to be smaller or equal to the smallest resistor that's in there. So we know that it's going to be, our RT is going to be equal to something less than 5 kilo ohms. So what do we end up getting for RT then? Yep, that's our inverse one, yep.
It's 2.5 gives it okay.
Yep, 2.5 kilo ohms. Okay, to save room on the board, I'm not going to use 4 digits, but you guys need to make sure you stay with the 4-digit rules. But otherwise, for me to write big enough, I kind of minimize my using the 4 digits sometimes. All right, so our RT then for the circuit then is going to be 2.5 kilo ohms. Yeah, I'm going to just erase this. This is the only time we're going to do this. We're not going to spell it out, but I just wanted you to see it so you've seen it. We're not gonna do it because we're gonna do it graphically. All right, so I have a total resistance of 2.5 kilo ohms, and now I also want to make sure I bring my test points back over. Did I lose any test points, or do I still have test points A and B? I still have them. Yep, because remember, it's just like me going right across the power supply. We didn't lose them, so we want to make sure we get our test points drawn in there. All right. So now we have our equivalent circuit. We got it down to one resistor. And now what we want to do is now we want to try figuring out everything we can. So this is chapter 3. So what do we know about our total resistance here? What do we know about RT now? What do we know about like for voltage? Do we know what the voltage is going across it? Yeah. And what's my voltage going to be? 100 volts. It's the only resistor that's in the circuit. And knowing Kirchhoff's voltage law, we know that the sum of all voltage drops must equal my source voltage. Since it's the only resistor in there, I know that I'm going to have 100 volts going across that resistor. And then if I know two things, can I figure out my current total? Yeah.
Divided by resistance.
Yep, so voltage divided by resistance. And so what's my current total going to be? 40 milliamps. Okay. Do I ask for power on this one? I think I do, don't I?
No.
Good. All right. All right. So we're not going to do power because otherwise that gets to be too messy. I think there's a couple of them I do. Yeah. But normally we like to find all four things about all our components and stuff. But also we throw power in there, and that just gets to be a lot of writing on the whiteboard here. All right. So we know all our three things that we need to know for this particular circuit. So what is really actually happening then is that this power supply is going to see a total voltage of 100. It's going to see a total resistance of the circuit as 2.5 kiloohms, and it's going to have 40 milliamps of current going through it. This power supply has no clue if this circuit is a single resistor or if it's actually looking at a whole network of circuits. It's one and the same. That power supply has no clue what's out there. All it knows is that it's got 40 milliamps of current, it's 100 volts, and the resistance of it is 2.5 kiloohms. So that's the equivalent circuit. So I can substitute that resistor in there and load down that power supply the same way with either one resistor or a whole network of resistors. And we're going to start looking more into that when we get into Thevenin's theorem and stuff like that, because that's important for us when we're designing circuits, of knowing what the impedance of the circuit is and what the impedance of the power supply is. All right, so once you get that, then our next step then is that we want to put in our test points back in. So what's going to be at test point A? Oh, the one thing we did forget is our ground. So test point B is the same as our ground, right? So my ground can be here, my ground can be here. Okay, anywhere along here can be my ground. So we all want to make sure you always put in your reference point. So we'll just put it over on the right-hand side. So what's going to be at test point A then for voltage? 100 volts. And is that the proper way we do test points? What do I always need for test points? Yeah, make sure you get your polarities. Don't forget your polarities, because I'll mark you wrong if you don't have polarities on your test points. So it's a positive 100 volts. Just bring your red lead down to your black lead. So assume this is my red lead, this is my black lead. The black lead never leaves, and I just bring my red lead down. Look at the first sign I see. It's a positive. Find out what my voltage drop is. So it's a positive 100 volts.
Is that what we write on the lines?
Yep, and then you can write those on the lines too. Yeah, but we'll come back. It's kind of jumping the gun here just a little bit. But yeah, you're correct. Okay, so then what's that test point B then? What's going to be my voltage at test point B?
Negative 100.
Plus or minus 0. Because if my red lead's going to go on B, my black lead's going to go on ground. Am I measuring any voltage? Nope. So I'm going to have, and again, all test points require polarity, so we just say plus or minus 0 volts. Okay? So now we have everything that we know about this equivalent circuit. We have our test points, we have our total current, we have our total voltage, and we have our total resistance. Now what we're going to do is we're going to take all this information that we have and we're going to bring it back over to that circuit. So we're going to go from this circuit to our first circuit. And this circuit, what type of circuit do we have here?
Parallel.
Parallel. So it remains constant in a parallel circuit. My 100 volts, my voltage remains constant. So that means I'm going to have how much voltage across R1 plus R2 plus R3? 100 volts. Okay, and then we're going to put in our 100 volts. Okay, so that's our first step. We're going to just analyze it going from a single resistor, then what type of circuit are we going to? We're going to a parallel circuit. then you just have to ask yourself the question, what remains constant in a parallel circuit? Voltage. And so you just put voltage all the way across there. Okay? Now, since we know two things, can we find the third?
Yep.
Yep. So what do I have for current going through R1 plus R2 plus R3?
10 milliamps.
10 milliamps. Okay? Then what do I have for current going through R4 and 5?
20 milliamps.
20 milliamps. Okay, one way of looking at it, just to double check your work, which one's going to have more current going through it? The 5 kilo ohm or the 10 kilo ohm?
5 milliamps.
The 5. It's got the least amount of resistance. If the R goes down, my current goes up. Even though I argue with Bob on that, but that was a whole other thing there. But
I was ahead of myself. And
well, I was a kind of a, I kind of threw Bob for a loop there because I was wrong. But I argued with Bob that said, no, that's not right. But we both knew it, but I was looking at it differently. Yeah, so when you're doing this, just double check your work constantly. Know that branch 2 is going to have the most amount of current going through it. And it's going to have twice as much current because it has half the resistance, so it's going to have twice as much current. So it's just one way of double checking our work as we're going along so we don't make any mistakes. We already know that we have another 10 kilo ohm resistor at 100 volts. And so we know that we got 10 milliamps a here. So how much current is going to have to go through this one? 10 milliamps. You don't even need to use your calculator again. All right, so now we know all three things that we need for this circuit. And then we know that, now we can also, we already figured out test points A and B, so we can just go ahead and transfer that information over. All right, so now we have all the information for that one. So now what we're going to do is now we're going to take all the information from here and bring it over to here. So what we're going to do is the first one we're going to look at is R1, 2, and 3. We said that was, how are those resistors? In series or in parallel? Series. Okay, so we're looking at, now we're just looking at this one resistor and we're going to break it out into the 3 resistors. So what remains constant in a series circuit?
Current.
Current. So if my current remains constant, I'm going to just take my 10 milliamps. And so how much current am I going to have going through R1? 10 milliamps. How much current through R2?
10 milliamps.
10 milliamps. And in R3? 10 milliamps. Okay? What's another name for a series circuit? Voltage divider. So now what we're going to do is we're going to take a look and calculate out our voltages. And find out how we divided up our voltages. So what's going to be my voltage across R1?
10 volts.
10 volts. And in R3 or R2?
30 volts.
30 volts. And 60 volts. Okay? I'm going to get rid of my boxes here so that myself some room here. Okay, so knowing that this is a series circuit, it's also a voltage divider, and then we know that the sums of all three of these voltages should equal what? 100, and does it?
Yep.
Yes. So always double check your work. So this is going to be my, this is my source voltage going into this series circuit. This is going to be my source voltage going into this series circuit. And then 100 volts is also going to be my source voltage going into R6 and 7. All right, so now we got that one, and then we'll go out, and before we come back to our test points, then what we're going to do is we're going to go out to R4 and 5. So how much current am I going to have going through R4? 20 milliamps. Then how about R5? 20 milliamps. Okay, so what's my voltage across R4?
60 volts.
60 volts. And then my voltage across R5? 40 volts. And if I add those two up, do I get my 100 volts?
Yep.
Yep. So we know we're probably doing good so far. Okay, then we're going to just break it out. We're going to go from this one resistor to another series circuit. We know that we got how much current going through our 6? 10 milliamps. And we have how much current going through our 7? 10 milliamps. My voltage across our 6?
70 volts.
70 volts. And my voltage going across our 7? 30. And if I add those two up, I get my 100 volts. Okay? So now we found everything that we need to know for that particular circuit. So we went down, combined all our like components that we could. If they were in series, we combined all those, brought them down to one resistor. Once we got them all into one parallel circuit, we could combine all those, and we got it down to one resistor, and then we just went backwards and Alright, so now our next step then is going to be to figure out our voltage drops for each test point. We already calculated out A and B, so we don't need to recalculate out that. So we know that we have plus 100 volts at test point A. We have plus and minus 0 volts at test point B. So now we're on C. So what do I have for what's my voltage at test point C?
At 90 volts.
What is it?
At 90 volts.
90 volts.
So that yeah.
Everyone agree with that?
Plus 90
Or are we
volts.
too sure?
No.
So let's take a look and see. So I'm going to
Plus.
grab my red lead. I'm going to use my blue one as my black lead. So my red lead goes on C. Where does my black lead go?
On ground.
On ground. That's right here. Okay? Anywhere along here. Okay? So I'll just bring it down over to here. Make it easy on myself. So I then just once I identify where that black lead goes, this one never moves. Then I just go ahead and I bring my red lead down to my black lead and I algebraically add it up. So the first sign I see is a positive 30 volts. Plus another positive 60 volts, I get what?
90 volts.
Positive 90 volts. Okay? So how about that test point D then? What am I going to get for voltage? Positive 60. Okay? How about test point E? What am I going to get? Positive 40. Just bring my red lead down to my black lead and add up the algebraically add it up. Or it's the same as me saying the voltage drop across R5. Or I could go ahead and I could go and make it difficult on myself, and I could go ahead and I could go up this way, down this way, and add it all up. As long as I came back down to my black lead, it wouldn't matter which route I went, it's always going to add up to my 40 volts. Okay, then how about test point F? What am I going to get? Positive 30 volts. Okay, just bringing my red lead down to my black lead. First sign I see is positive 30 volts. Oh, I want to make it tough on myself. I could go add a negative 70 plus another positive 60, so that gives me negative 10 so far. Come back down and then add another positive 40. Will give me a positive 30 volts. Again, it doesn't matter which way I go, it's just as long as I bring my red lead down to my black lead. Doesn't matter which path, I can go around it 5 times. As long as I correctly add it up algebraically, it'll come up to whatever that test point is. Alright. So any questions on that so far? Pretty straightforward? Yep. Alright, I'm going to erase this half. No one has any questions, and we'll... Alright, then on the next page there, it has a whole bunch of, so basically we already filled out all that information. We know, so how much current is going through branch 1?
10 million.
10 milliamps. And the current going through branch 2? 20 milliamps. And then branch 3 is going to be our 10 milliamps. Then our voltage across branch 1 is going to be what? So how much voltage do we have going across branch 1? 100 volts. And then our voltage going across branch 2, 100 volts. And then 100 volts also going across branch 3. Okay? Our RT and IT and ET, we all calculated out over on our very first circuit all the way down to the 1 resistor there. So we had 100 volts, we had 40 milliamps, and we had a 2.5 kiloohms of resistance. All right, so then, so what do I get then for our, so now I'm on the second page there. So what do I get for test point VAB? Plus 100 volts. We already calculated that because our V is the same as our ground. Okay? What do I get for voltage from VAC? What's that going to equal? So where's my red lead go? On A. And my black lead goes where? C. So here's my, so my red lead goes on A, my black lead goes on C, which is right here. All I have to do now is just bring my red lead over to my black lead. Just follow that wire. I don't have to follow my current path, I just have to follow the wire, follow the current, follow one of the paths, come down, first sign I see is positive. And my voltage drop is what? 10 volts. So the voltage across A to C is going to equal what? Positive 10 volts. Okay, then we have C to D. What's voltage from C to D? Plus 30 volts. Let's just double check if Jesse's right. So my first, my red lead goes where? On C. Black lead goes where? On D, right here. So basically all I'm measuring is my voltage drop across to R2. So I'll bring my red lead down to my black lead. First sign I see is positive. My voltage drop, 30 volts. So positive 30 volts. Okay, then how about from E to B? So my red lead goes where?
60.
Okay, my red lead goes on
D.
on B.
D.
All right. And then my red lead, my black lead goes where?
B.
B. So basically I'm just measuring my voltage drop across R3. So I'm going to get a what?
Positive 60.
Positive 60 volts. All right, and from A to E.
Positive 60.
Positive 60 volts. So red lead goes on A, black lead goes on E. Right? Was that right? A to E, so it would be one here, right? So the first sign I see is positive. Look at my voltage drop. It's going to be a positive 60 volts. All right, so A to E. How about E to B?
What's 40 volts?
Oh, he's just covered.
Alright.
So E to B, what do I end up getting?
Plus 40 volts.
Positive 40 volts. So from here, we already identified what it is. It's already positive 40 volts if you want to look at it that way. Otherwise, just bring your red lead down to your black lead. Okay, then E to B, then we got A to F. Positive 70. Okay, so that's our voltage drop across R6. F to B.
Plus 30 volts.
So my red lead goes where? So where does my red lead go?
F.
F. Black lead goes on B, which is the same as my ground. We already identified it that it's a positive 30 volts. Okay, then how about C to B?
Plus 90 volts. Plus 90 volts.
So it's the same as test point C, so you're going to get a plus 90 volts. C to E?
Minus 20 volts.
Plus 50 volts.
So C to E. So my red lead goes where?
This point C.
C. My black lead goes where?
E.
On E, right?
Yep.
Yeah.
So if you go
Okay.
down,
So you go.
So then,
Doesn't matter which way you go.
yeah, I know.
it doesn't matter which way you go. Yeah. So this way here, I only have to go through 2 resistors. I go through here. So I'm going to have my first sign I see is a negative 10 volts plus a positive 60 volts gives me what?
Positive 50 volts.
Plus 50 volts. Okay, then there's also another way that we can do it. Okay. What's my, if I have my red lead on C, my black lead on E,
Oh, that's right.
what's my voltage potential between these 2 test points? Okay, remember now my test point is my plus 90 volts and my plus 40 volts. So what's my voltage potential between
50
a
volts.
positive 90 and a positive 40?
50. Positive 50 volts.
50 volts. Okay? So now we're looking at the red lead. Is my red lead more positive than my black lead, or is it more negative than my red lead?
More positive.
It's more positive. So then I would end up with a positive 50 volts going across C to E. Okay? So then we don't even need to go ahead and bring our red lead around to our black lead, but it is a good way of double checking it. Okay, so we're just looking at what is that voltage potential, because that's what's going to determine when we're working with solid state devices. Remember, all these test points, these are just outputs. Okay? They're not just reference points. They can be used for either troubleshooting or they can be used for outputs going into our solid state devices. And to determine whether if our solid state device is turned on, we need to know, is it more positive or more negative than the other one? So we might be referencing 2 different voltages going into our transistors. All right. So that'll be coming up in the spring semester. So now we have D to E.
It's positive 20.
Okay, so I got my red lead on D right here, my black lead on E. So the voltage potential between positive 60 and positive 40 is how many volts?
20.
20 volts. Which one's more? Is my red lead more positive or more negative than my
Red positive.
more positive? So I'm going to have my positive 20 volts. All right, then how about E to D?
Negative 20 volts.
Negative 20. So let's just take a look at that one. So now when we put our red lead on E, put my black lead on D, my voltage potential between the 2 points are what? 20 volts. That doesn't change. But now I look at my red lead. Is this one more positive or more negative than my black lead?
More negative.
It's more negative. So then we just tell ourselves it's more negative, and so now we're going to end up with a negative 20 volts. And all we did is just swapped our 2 leads around. All right, how about E to F? So what is it, positive 10? Okay. Then how about F to E?
Negative 10.
Negative 10. We just flipped our leads around. So if I need negative 10 volts, I just swap my 2 leads around. D to F.
So, plus 30 volts.
So D to F is going to be a plus 30 volts. Put my red lead on D. Put my black lead on F. Find out what my voltage potential is, the difference between the 2 points. That's 30 volts. Look at my red lead. Is it more positive than my black lead? Yep. So it's going to be a positive 30 volts. All right. Then how about F to D? Negative 30. And F to C,
Negative 60.
F to C, so would be negative 60. Negative 60 volts then. All right.
Good. I think this is the one that really stumped us last semester.
I know,
Spring, yeah.
that normally throws a lot of people
Some
off.
of the hardest.
Yeah. Yeah. It isn't so bad as long as you just follow the rules and then trying to combine your circuits the right way. All right, any questions on the first circuit then? Okay. So this is what we call, this one's really what we call a parallel series because we have parallel branches and then we have series resistors within it. So this is really called a parallel series, but in general we always just call them series parallel circuits. But if somebody does call it as a parallel series circuit, that's what this is. This is that style. All right, let's take a look at the next one here. All right, now we do have a true series parallel circuit because we have R1, which is in series with R2, 3, and 4. Okay? So things change a little bit more when now we put that series resistor in there. So let's take a look at it. So again, what we want to do is we want to get down to one single resistor. All right, what's the first step that I want to do before I, yeah, draw my polarities and my current path in there. So I'm going to start out negative, positive. So all my current is going to be coming out of my power supply. All my current is going through M1, so we already know that M1 is my total current. And I want polarities. Remember, we have to break the circuit. Wherever we break the circuit, we replace it with a current meter. So that all the current goes through the current meter, then back out of the current meter and back into my circuit. So all my current is going to be coming out of M1, then it's going to go into my first current node. So all my current is going to go through M2, and then the remainder is going to go through to this current node. Some of it's going to drop off this way, and the remainder is going to go up through this way. So then my current is going to go through this one, into that current node, up through here. And then the current coming out of R4 is going to combine with the current of R3. Those two currents are going to combine together, join in with the current of R2, and combine together. And then all my current then, now, because we said that all my current came in and it divided up amongst all three of them, then all three of them combined back together again, so that means I have my total current going into M5. And then I have my total current going through R1. And then back into my source. Okay? So that's what we kind of like to talk ourselves way through it. Got all my current coming out of my power supply. It's going to divide up three ways. All the currents are going to combine back together. My total current is going to go back in through M5. That means that my total current has to go through R1 and then back into my power supply. Okay, so now I got my current paths and polarities. Then what's my next step that I want to do?
Draw your sketching for the circuit.
See what's that?
What you want to do? You could put in your numbers or whatever. Don't let you know.
Yeah, we already know that, but it's I think all we know is the resistance, right?
Yep.
And voltage.
And the voltage. So yeah, we should probably so we can see that. We should do that on our circuit. So we know our voltage is what? 100 volts.
100 volts.
And R2 is what?
R1.
R1 is
R1 is what?
47 ohms.
27 ohms.
47.
47. Okay, R2,
33.
33 ohms. R3,
68.
8 ohms. And R4,
22.
22. Alright, good. Alright, then what's my next step?
Draw your equivalent circuit.
Now we're going to draw our equivalent circuit. So we know that we're always going to want a straight line. This time we are not straight line because we have a component that's horizontally. We like to have all our components, if possible, vertically. So what we're going to do is that we're going to straight line the circuit first before we even do our equivalent circuit. So what we want to do is we want to put our power supply on the left-hand side. And we're going to follow the current path. That's the easiest way. So I know that all my current is going to come out of my power supply. And then we said that we're going to branch off into these three circuits. So what I like to do is that I like to force myself to go up. I just automatically, the minute I start trying to draw myself a straight line, I want to force myself to go up. So I do that. Then if I come into a branch and I know that I'm going to branch off into three, then what I do is I make myself my branches. 1, 2, 3. Okay, then I know that I'm going to be going through R2. I'm going to go through R3, and I'm going to go through R4. So I'm taking all my current that came in, I got all my current coming through, so that's why I like to make it out with branches. So I got all my current coming into this branch. Then it's going to divide up amongst the three, then go up, and then all those three then are going to come back, and then they're going to combine together again. So then I'm going to combine all those together. Then I like to come out with a single one so I can see my currents going through, so I can understand what's going on with my current. And then my total current then is going to go through my current meter, and then it's also going to go through R1. So then I know that I have my total current going through R1. And then I'm going to come back down. And just to save room on I left the ammeters out there. You don't need to put the ammeters in there. We're just going to use those for reference so we understand what the current is going through there. But to save room, I did it that way. So I'm going to relabel them. So here's R1, and that was 47 ohms. R2 was 33 ohms.
68.
68 ohms.
22.
And 22. Redrawing my current paths and polarities. So I got all my current coming down, coming through. It's going to come into this first branch. It's going to split off. Some's going to go this way, some's going to go this way, and some's going to go this way. This is going to continue on this way, combine into here. That current is going to combine. All three of those currents are going to combine and then go through R1 and then back into my power supply. All right, so now we have our line, straight line. So when I say that I want something straight line, this is what I expect to see. Power supply on the left-hand side, and then all our components drawn vertically, if possible, on the right-hand side. And we better get our voltage in there too. We got 100 volts. Okay? So no test points on this one, so we don't have to worry about that. So I think we copied over all the information that we need so far. All right, so now so this circuit is the exact same thing as that circuit. It's just drawn differently, and it should be a little easier to see what's going on. Once we do that, we should understand what's going on with the circuit. So now what we want to do is we want to start reducing our circuits down. So which ones can I combine first?
The R2, R3.
Yeah, so I want to combine R2, R3, and R4, and those are all in what type of circuit?
Parallel.
Parallel. So what I'm going to do is I'm going to redraw